convert to design a heat engine which is exchanging heat with a single thermal reservoir and converting all the heat that is received by it totally into the work output. That means the heat engine is not rejecting any heat, thereby converting all the heat that it is taken by it totally into the work output. Nobody could manufacture or make such a heat engine. The actual heat engine, which is possible according to the Kelvin-Planck statement of second law of thermodynamics, is which should be able to work between two temperatures or two reservoirs at two different temperatures, namely high temperature reservoir and low temperature reservoir. From high temperature reservoir, it is receiving heat and converting a part of that into work. The remaining heat it is rejecting to the low temperature reservoir, which is also known as sink. High temperature reservoir is also known as source of heat. Only such heat engine is possible to make out according to the second law of thermodynamics. The into mark what I had given above, it is meaning that the cyclic heat engine working or exchanging with a single thermal reservoir and completely converting whatever the heat supplied to it totally into work output is not possible. That is the meaning of into. The tick mark in the second heat engine means that only it is possible to make such a heat engine which is receiving heat from a high temperature reservoir and converting a part of it into the work and rejecting the remaining heat to the low temperature reservoir, which is also known as sink. Now, defining thermal efficiency of heat engine. It is defined as the ratio between net work output of engine and heat supplied to heat engine. Thermal efficiency of heat engine is net output divided by QS. Since according to first law of thermodynamics, which states cyclic integral of delta Q is equal to cyclic integral of delta W, net work output of heat engine working in a cyclic process is equal to heat supplied to the engine minus Q rejected. So many kilojoules per cycle. So, thermal efficiency of heat engine cycle is equal to QS minus QR, which is nothing but net work output divided by QS. That is 1 minus QR by QS. Let us write the modulus symbols for both rejection and supply, because whatever may be the sign allotted to the heat transfer, modulus always mean a positive sign. Since heat rejected by heat engine is always greater than 0 according to Kelvin Planck statement of second law, thermal efficiency of any heat engine is always less than 1 or 100%. So, it is not possible to make a heat engine having 100% thermal efficiency according to Kelvin Planck statement. Now, coming to the Clausius statement of second law of thermodynamics, it is stated as, it is impossible to construct a device operating in a cyclic process which will produce no effect other than the transfer of heat from a low temperature thermal reservoir to high temperature thermal reservoir. Pictorially, it can be seen as, it is not possible. The into mark shows that it is not possible to manufacture such a device which is not producing any other effect other than the transfer of heat from low temperature reservoir to high temperature reservoir. Or it can also be stated as, heat will never flow from low temperature to high temperature without the aid of external agency or input. So, according to the Clausius statement of second law, it is just possible to design a cyclic device which is transferring heat from low temperature reservoir to high temperature reservoir heat can be transferred from low temperature reservoir to high temperature reservoir only with some external agency or energy input or either in the form of heat or work. Only such device is practically feasible. That is the reason why the tick mark is given. The examples for Clausius statement are, number 1, refrigerator or air conditioner. A refrigerator is a cyclic device which is transferring heat from low temperature to high temperature Q absorbed is the heat taken from the low temperature and Q rejection is the heat rejected to the high temperature. The device is refrigerator. It needs mechanical shaft work input which is supplied by the motor driven by electric power supply. Similarly, the other example that could be given is heat pump. A heat pump is a cyclic device which is transferring heat from low temperature to high temperature with the help of mechanical work input. Q rejected is the heat rejected to the high temperature. Q absorbed is the heat absorbed from the low temperature. Even though both heat pump and refrigerator are doing the same thing, the useful effect in a heat pump is Q rejected to high temperature reservoir, whereas useful effect or the effect sought after in a refrigerator is Q absorbed or heat absorbed from low temperature reservoir, abbreviated as LTR. Defining coefficient of performance for these two devices, that is for refrigerator and heat pump, which are the examples considered regarding Clausius statement. COP of refrigerator is defined as the ratio between heat absorbed from low temperature reservoir divided by work input given to the refrigerator. Similarly, coefficient of performance of heat pump is defined as heat rejected to high temperature reservoir divided by work input. Here it is important to note that refrigerator always tries to maintain a low temperature with respect to the hotter surroundings, whereas heat pump would always like to maintain a high temperature with respect to the colder environment. In the cold countries where the ambient temperature will be around -30 or -40 degrees centigrade, a heat pump is used to maintain a constant room temperature or comfortable temperature of 25 Celsius by absorbing the heat from the very cold environment which is prevailing outside the room. Both the statements of Kelvin-Planck and Clausius statements of second law of thermodynamics are equivalent, that is violation of one statement automatically leads to the violation of the other. That is, if we think that Kelvin-Planck statement is violated, it will automatically result in the violation of the Clausius statement, and vice versa. That is the meaning of equivalence of the two statements. Writing the first law of thermodynamics, to either refrigerator or heat pump, that is cyclic integral of delta Q is equal to cyclic integral of W. That is first law applied to the cyclic process. It results in Q rejected to high temperature reservoir is equal to Q absorbed from low temperature reservoir plus work input. This equation or first law is applicable to both refrigerator and heat pump even when they are irreversible or reversible. Irrespective of reversible heat engine or irrespective of irreversible heat pump or irreversible refrigerator, this equation holds good for both refrigerator and heat pump. A small problem could be worked out here for a refrigerator. I suppose a refrigerator is rejecting 100 kilojoules of heat to high temperature by taking work input of 70 kilojoules by absorbing heat from a low temperature reservoir. Then COP of refrigerator is how much? Applying first law of thermodynamics to the problem, Q rejected is equal to Q absorbed plus work input, that is 100 kilojoules, that is heat rejected, is equal to Q absorbed plus 70 kilojoules, implies Q absorbed is equal to 100 minus 70, that is 30 kilojoules. Therefore, COP of refrigerator is 30, that is Q absorbed divided by 70, that is a work input, that is 3 by 7. Many people would have a misconception that because thermal efficiency of a heat engine is always less than 1 according to the Kelvin-Planck statement, they think that COP would always be greater than 1. It is not so, because COP may have any value, may be greater than 1 or less than 1.